Hello students, today we will see Hall effect and the derivation of expression of Hall coefficient. So first of all we will see Hall effect. So what is Hall effect? When magnetic field is applied perpendicular to the current carrying semiconductor or conductor, potential difference is developed in the direction perpendicular to both current and magnetic field. This phenomena is known as Hall effect. So why Hall effect? What is the importance, advantages of Hall effect? So first important point is the Hall effect used to determine the sign of charge carriers, means it is used to identify the semiconducting material whether it is n-type or p-type. Second important point is that it is used to determine the charge carrier concentration, means it is used to determine the concentration of holes and electrons in semiconducting material. Third important point is that the Hall effect is used to determine the mobility of charge carriers, means the ability of the movement of charge carriers can be easily determined by Hall effect if conductivity of material is known. So these are the importance or advantages of Hall effect. Now we will see detailed explanation regarding Hall effect, and from that description or explanation we will derive the expression for Hall coefficient of semiconducting material. So suppose this is the n-type semiconducting material and suppose this is the slab of semiconducting material. So we have applied a voltage through this semiconducting material and the current is passing through this semiconducting slab. Okay, so this is the direction of current and the direction of current is in positive x direction. Okay, suppose this semiconducting material slab having thickness d and width, let t be the width of this semiconducting slab. So t be the width and d be the thickness of this semiconducting material. Okay, suppose magnetic field B is applied in positive z direction. So this is the direction of magnetic field. Since this is an n-type of semiconducting material, so charge carriers are electrons. Okay, suppose the charge carriers are electron is, suppose this is one of the electron. Okay, so these electrons are drifted in negative x direction, and suppose vd with the drift velocity of this electron. Since magnetic field is applied in z direction, okay, so therefore the force due to magnetic field is acting along negative y direction. Okay, so this is the direction of magnetic force, and due to that magnetic force, the charge carriers, that is electrons, are bending towards the lower face of the semiconducting material. So which is the lower phase? Lower phase is OABC. Okay, so electrons are bending down towards the lower phase, and due to those electrons, the net negative charge developed on the lower surface of this semiconducting slab OABC, and because of that the net negative charge developed on lower surface, so oppositely the net positive charge will be developed on the upper surface of this semiconducting material EFGD. Okay, so because of this separation of this net positive and negative charges, the strong electric field developed between these two phases, upper and lower phase, and the direction of this electric field is also known as Hall electric field, and the direction of this Hall electric field is negative y direction. Okay, and because of that a strong potential difference developed between these two phases. Okay, this potential difference is known as Hall voltage and can be represented by this symbol VH. Okay, so because of that electric field developed between the two phases in negative y direction, so the electric force due to these electric fields will act in upward plus y direction, and because of that electric force, again those electron, okay, will be moved towards upward direction. When this electric and magnetic field become equal, then the flow of electron will stop. It means that electron will move in their original path. Okay, so this is the description regarding this diagram. Okay, whatever we have seen in this diagram, we have quoted on the slide. Consider a rectangular slab of n-type semiconductor of width t and thickness d, and let magnetic field is applied along plus z direction, And since it is n-type semiconductor, charge carriers are electrons, and we have applied I. This is I is flowing in plus x direction, and electrons are drifted in minus x direction. Vd with the drift velocity of electron. And we know that the magnetic force acts in negative y direction. It results electron to bend downwards towards face ABCO, and net negative charge. Okay, net negative charge, this means electron accumulate on the lower surface, producing net negative charge, and as a result positive charge developed on upper surface, EFGD. Okay, as we seen in the diagram. So therefore electric field is set up between two faces, okay, downward minus y direction, and this electric field is known as Hall electric field and represented by symbol EH. And potential difference developed between two faces is known as Hall voltage, and it is represented by symbol VH. Okay, the important condition is that when electron flow towards lower surface will stop. When will stop, or when will it will flow? That electron will flow in their original direction when force due to magnetic and electric field will equal or balance each other. Okay, when force due to magnetic field, that is Fm, and force due to Hall electric field, that is Fe, is equal, balance each other, then the flow of electron will stop. It means that electron flow in their original path. So this is the condition. Fm is equal to Fe. Fm is the force due to magnetic field, Fe is the force due to electric field. Okay, we have given in the magnitude term, we have removed the vectors because we have represented in the magnitude. Okay, so what is Fm? Fm is Be into velocity, drift velocity. We know that the magnetic force is Be into Vd. So Vd is drift velocity, is the charge of charge carriers, and B is the magnetic field, and force due to electric field, we know that E, charge into electric field, that is Hall electric field, EH. Okay, now E, this is Vd is drift velocity, E cancel out. So from that we can easily determine drift velocity. Okay, BVD is equal to EH, and EH is equal to B into Vd. Suppose this is equation number 1. B is magnetic field, Vd is drift velocity, EH is Hall electric field. Now potential difference, that is Hall voltage. We know that what is the formula for potential difference is nothing but electric field into the separation between two faces, that is D. Okay, so VH is equal to EH into D. So this is the Hall voltage or potential difference. So Hall voltage VH is equal to, we know that EH is from equation number 1, B into Vd. So Hall voltage is equal to B into Vd into D. D is the thickness of the slab. It means separation between upper and lower faces. So this is suppose equation number 2. Okay, now we will derive Hall coefficient. First of all, we will see the definition of Hall coefficient. What is Hall coefficient? Then we will derive the expression of Hall coefficient. So simply Hall coefficient is defined as Hall electric field per current density per magnetic field. Means Hall coefficient is, okay, the symbol for Hall coefficient is RH is equal to EH divided by J into B. J is current density, B is magnetic field, EH is Hall electric field. So Hall coefficient is Hall electric field per current density per magnetic field. So this is the simple formula for Hall coefficient. Now we will derive this formula. Okay, we will see the derivation of expression of Hall coefficient. Okay, we know that current density is given by this formula. Current density is equal to NeVd. E is the charge on charge carriers. Okay, suppose charge carriers are electron, so charge on electrons. N is the charge carrier density. Okay, and Vd is nothing but the drift velocity. So J is equal to NeVd. Okay, so Vd, from this we can determine Vd. Ne we have taken to that side, so Vd is equal to J by Ne. Vd is equal to J by Ne, and Vd is nothing but Eh by B. So since drift velocity is Eh by B, we have seen in earlier slide. Okay, so Vd is equal to Eh by B is equal to J by Ne. Okay, so J, we have shifted J to that side. Again I am showing that expression. We have shifted cross multiplication J to that side. So we'll get EH by JB is equal to 1 by NE. Okay, suppose this is equation number 3, and equation number 3 is Hall coefficient is nothing but 1 by NE. So all the second formula for Hall coefficient is equal to, RH is equal to 1 by NE. So this 1 by NE means Hall coefficient. So above equation will become n is the density of charge carriers, holes or electrons. If charge carriers are electrons, then n is density of electrons. If charge carriers are holes, then n is the density of holes. So RH is equal to 1 by Ne. So in plus of 1 by Ne in this equation we can put RH. So we will get, since RH is equal to EH by JB, so we will get RH is equal to EH by JB, and EH means Hall electric field, that is nothing but VH by D. The formula for electric field is potential difference divided by the separation, that is D, and current density is nothing but current per unit cross sectional area. So current density J is equal to I by A. Okay, so again electric field is Hall voltage divided by D, and current density is current per unit cross sectional area, so I by A, I by A. Now cross sectional area of that semiconducting slab. So how to calculate the cross sectional area? Again I am showing that diagram. Okay, again I am showing that diagram. So this is the diagram, and cross sectional area means this area. Okay, the opening of that. Okay, because current is passing through the cross sectional area. So cross sectional area is this. So how to calculate the area of this? Okay, this width into thickness, T into D. Okay, by multiplying D, matlab this difference is D, this side GB is D and BC is T. T into D will get the cross sectional area of this rectangular semiconducting slab. So cross sectional area is D into T. Oh, okay, so cross sectional area in place of area, okay, D into T, D into T, this is the cross sectional area, area thickness into width, D into T. Okay, now this dt will go to the numerator, and Vh is, will get Ib into D, so dd will be cancelled. So we will get Hall coefficient is equal to Vht divided by I into B. Vh Hall voltage, T is width of this semiconducting slab, I is current passing through that slab, B is magnetic field. Okay, so this is the standard formula to determine the Hall coefficient. This is the experimental formula to determine the Hall coefficient. Okay, we can use this formula in lab to determine the Hall coefficient of semiconducting material. So we have to calculate the potential difference. Okay, thickness is known, current passing through that slab, okay, and this magnetic field. So by determining T, I, B and VH, Hall coefficient can be easily determined. Okay, so this is the expression for Hall coefficient. Okay, now we will go for the Hall mobility. Okay, we will derive the expression for Hall mobility, and we know that the product of conductivity and Hall coefficient is nothing but the Hall mobility. So conductivity is sigma and Hall coefficient is RH. So the product of sigma and RH is nothing but the Hall mobility, okay, which is determined by the symbol mu. Now we will prove this. Okay, derivation of expression for Hall mobility. We know that the conductivity of semiconducting material is Ne. Mu is charge on charge carriers, N is the charge carrier density, and mu is mobility. So if I bring Ne to that side, okay, so sigma by Ne is equal to mu. Now I bring sigma to that side. So 1 by Ne is equal to mu by sigma, and 1 by Ne is nothing but the Hall coefficient RH. So RH is equal to mu by sigma. So this is mu is equal to sigma into RH. So this is the formula for Hall mobility. So this is the expression for Hall mobility. So today we have seen the expression for Hall mobility, derivation of Hall coefficient, and this is the important experimental formula to determine the Hall coefficient. Okay, and we have seen Hall effect, what is Hall effect, and the detailed explanation regarding Hall effect. So that's all for today. Thank you very much.